Alright, in this video we're going to go through numbers 1 through 5 in your Chapter 7 FRQ assignment, and really this is just one FRQ that's been split up into a couple different questions for ease of use with Schoology. So here we have a differential equation given to us, and we're asked to sketch a couple points for the slope field. Like I've done in a couple of the other videos, what I like to do to be a little more organized here is just make a table. So I'm going to plug in my points, x, comma, y, and then I'm going to say, okay, well, what's the slope at that point? What is dy dx at that point? We'll just go through. I'm going to start with 0, -1. And certainly you don't need to show all this work. This is just me being organized in terms of an explanation. All we have to show is the slopes. So if I plug in 0, -1, I'm going to get out 1, so that's a slope of 1. Then I plug in 0, 1, positive 1 now, and I'm going to get -1. And then 0, 2, and I'm going to get out -2. So let's go ahead and draw those slopes. So at 0, -1, we've got a slope of positive 1. And as we've said in the past, just kind of do your best, make it look reasonable and relative. My slope of -2 should be steeper than my slope of -1. That's all we're really looking for. Now we'll do the same thing when we have our other 3 points where x is 1 for all of these. So now I've got 1, -1, negative. There we go. And so I get 3 if I plug that in. And then 1, 1. And that's going to be positive 1. And then 1, 2, well, that's going to be 0. So graph all those 3. So positive 3, positive 1, 0. Kind of make that one, fudge that a little bit. And that's all we're looking for there. Okay, so then the next part of this question. So if we look at this differential equation, now they want us to find the second derivative. It's been a while since, we don't see this notation as much for second derivative, but remember that does just mean second derivative. Originally this is an FRQ, this is not multiple choice, but I felt like this was the best way to handle this question was to make that multiple choice for this Schoology version of this. All we would do is just take the second derivative, so we do that. So when I take the second derivative, second derivative with respect to x both times, derivative of 2x is just 2. Derivative of y, if I wanted to, I'm thinking about this as implicit differentiation. So I think about, well, what's the derivative of any one variable by itself? Well, that's just 1, in this case -1. But then because I'm supposed to be differentiating with respect to x, and this is not an x, I have to put a dy dx with it. It's that implied chain rule, why we call it implicit differentiation. So I need a 1 dy dx. Now, that is actually this answer right here. The last one here on this version of it, those will shuffle when you take it. But that's not the right answer because the directions say in terms of x and y, which means I cannot have this dy dx in my answer. So what do? Well, dy dx equals 2x minus y. So we plug that in. So just take this, plug it in for that dy dx. 2 minus 2x minus y. And then we distribute and we get 2 minus 2x plus y. And that would be this one. there's our answer to that. And on to the next piece. Okay, so in this case, using that same differential equation again, same one. Now they're saying, okay, it's dropped down, and they want to know about the concavity of this curve in the second quadrant. And this is kind of set up for us to be able to give some explanations here because we've got the because. Again, on the regular FRQ, this wouldn't be dropped down. It would just ask us about the concavity in the second quadrant. But I've kind of tried to make it a little easier for this to grade in Schoology and give you that more live feedback. It's kind of my goal here. So if we're talking about concavity, we're talking about the second derivative, and isn't that nice because we just took the second derivative. So we said that our second derivative was negative 2x plus y plus 2. And they're asking us specifically here about the second quadrant. And over here we can see in the drop down we're saying when x is something 0 and y is something 0 as well. So in the second quadrant, if I think about that second quadrant, quadrant 2, x is negative over here and y is positive. So if I think about plugging those things in, negative x's and positive y's, if I plug in a negative x here, then multiplying that negative x times negative 2 is going to give me a positive. If y is positive and I'm adding it, then I'm adding a positive, and of course plus 2. So this is going to be positive. Oops, sorry, I forgot my 2 there. So my second derivative is going to be positive. So my second derivative is going to be positive when x is negative and y is positive, thus making us concave up, because the second derivative is positive. All right, on to the next part. Oop. Guess we're going down this way now. So this one's a little bit interesting. I have to think really carefully about what it means for something to be a solution to a differential equation. So we have our same differential equation we've been working with this whole time, and now it says what could m and b be, or possible values for m and b, such that y equals mx plus b is a solution to that differential equation. Which of course being a solution means when we plug in that equation and its derivatives into the differential equation, it makes the statement true. So this differential equation only has y and the first derivative in it. We have y. Now we need the first derivative so that we can plug it in. You know, just like in some of the other problems, we want to know, is this potential equation a solution? Well, you take the derivative, you take the second derivative, you plug those pieces in, and you see if it makes the differential equation true. So we're going to do the same thing here. So given this equation, the derivative of that, dy dx, is just m. That's the derivative, and also, I mean, that's obvious because it's just the slope, and a line has constant slope. So I can take this equation and make it now, okay, now we're going to take this one and we're going to think about this. Well, this means, come over to the other side, well, dy dx is m equals 2x minus y. But y is mx plus b. So let's follow this again here. First, we said, okay, if this is my equation, y equals mx plus b, then dy dx is m. Now, if we take that and plug it in to this equation, well, then dy dx is m, just substituting. Leave the 2x as it is, and then replace y with this equation y here. Now, if we just kind of combine some like terms and clean this up just a little bit, leave the m, leave the 2x, distribute. We've now got minus mx minus b. And now I'm going to do something a little bit sneaky algebra-wise here. If I factor out an x, so let's pull out an x from this first chunk here. I'm going to get 2 minus m minus b. Now, the left and the right side have to be equal because the problem says that they are. We're looking for this to be a solution. It says they are equal. So these things have to be equal. This isn't one of those where we're checking to see if it is equal. They have to be. Well, there's no x over here. If there's no x on the left side, there can be no x on the right side, which means this thing has to be 0. Because if that's 0, then I have 0x. So 2 minus m must equal 0. In other words, m must equal 2. Now, if this whole thing is 0, which it has to be because there's no x's on the left, then that means my equation becomes m equals the opposite of b. Well, we just said that m was 2. So 2 equals the opposite of b, and negative 2 equals b. And those are our values. M is 2, and b is negative 2. Kind of a sneaky one there. Often we'll see that I feel like some of the earlier parts of this FRQ were a little more straightforward, and so this last part is a little trickier. You often have a little bit of a balance there.